All right. Good morning, you guys. Happy Friday to you. Kind of crazy to think how far we've come. If my math is correct, I believe we are 10 weeks into our remote learning experience. So it's pretty wild that we've been at this for as long as we have. I want to thank you guys for sticking with me and continuing to push forward. Like I mentioned the other day, this is really going to benefit you guys if you end up taking a college Calc course. I truly believe that. So thanks for pushing through. We got 1 week left, so let's just finish strong, okay? What we're going to finish out this week with is section 5.2 still, but we're going to look at a little bit different substitution, okay? And this is really when substitution is going to actually kind of make a little bit more sense in terms of why we call it substitution. So to this point, basically what you've seen is sort of the idea of substitution is we have to have a function and its derivative, okay? So we can kind of pull off to the side and we call it typically u, where we call our larger function u, and then we hope that the other portion of it is its derivative, okay? So what I want to show you is I want to show you a little bit of an odd problem that you're going to run into today. And by the way, I should mention before I forget, the second portion of the assignment is going to literally pick right back up where we left off on Wednesday. So you're going to pick up with number 19, I think it is. It's in the middle of an actual section. So the directions are going to say find each integral. When you get to a new portion of your assignment today, I don't have my book open right now, but the directions say something kind of goofy. Don't worry about what the directions say until you get to the last 4 questions, okay? When you're going through your assignment, everything except for the last 4, you're going to find the integral the same way we've been doing, okay? It's when you get to the last 4 that something weird is going to happen. It's going to say something like use true substitution. I can't remember exactly what the words are, but you're going to see the difference when we get into examples 2 and 3 compared to example 1, okay? So off to the side here, I'm just going to point this out. If we want to call our original function u, it's got to be the larger function. So it's negative 3x squared minus 3x plus 7. And the derivative of u with respect to x, so du dx, when we look at it, it's going to be a little bit different than what we have here. The derivative would be negative 6x minus 3, okay? So what I want to point out here is this. It's a little bit different than what we have here, which is the 2x plus 1. But if we factor out a negative 3, negative 6 divided by negative 3 is 2, and negative 3 divided by negative 3 is positive 1. So now you can see it is just a coefficient different from what we have in our expression up here. So it is the 2x plus 1, but with a negative 3. So you're going to run into this a little bit on your assignment early on, where you just have to counter, you have to make up for that negative 3 with the fraction that will wipe it out, which is negative 1/3. So essentially, all we have to do on this one is we can kind of ignore this other piece, focus on integrating this portion, which is pretty easy. It's just the polynomial raised to the first power, but we have to make up for it with a negative 1/3, okay? So it's negative 1/3, and then we take this whole polynomial, negative 3x squared minus 3x plus 7, increase its exponent by 1, so bump it up to a 2, and then put it over a 2, and then go from there as far as cleanup goes, right? So if we take negative 1/3, okay, I'm going to pull this 2 kind of outside here. Negative 1/3 divided by 2 is the same thing as negative 1/3 times a half. So that would be negative 1/6. And then the negative 3x squared minus 3x plus 7 squared. This is the way the back of the book will show it. If we want to write it as a true function, we'd say f of x equals negative 1/6 with all that stuff. So the bulk of your assignment today is very similar to what you had on Wednesday, okay? Where you're going to have an original function. If you call it u, its derivative is either going to be represented by the second part of the expression, or it's going to be a coefficient different. Okay, the only thing different between the two is there's a coefficient in front of it until you get to the last 4 questions, okay? Because the last 4 questions are going to look like examples 2 and 3, okay? Where your larger expression in this example is 2x minus 1. So if we want to use, and again, I don't remember what the directions specifically say, but it's something to the effect of use true substitution. You actually have to do genuine substitution here. So we're going to call u 2x minus 1. However, when you look at this, 2x minus 1 is this expression. The derivative of that is just 2. So now there's an actual variable difference, okay? Like your derivative is just the number 2, but your other expression is also an x. So it's very different than up here where the only thing separating my derivative and the other part of my expression was a coefficient. Now there's actually a variable difference, okay? So I'm going to show you a couple things and it's going to be a little bit strange to you, but all it is just basic manipulation. So take this equation right here that says I'm going to represent my u, my original function, as 2x minus 1, and I'm going to solve that for x. So I'm going to add 1 over here to u, and then I'm going to divide by 2 so that I get x by itself. So you'll see why in just a second here. So it's going to be u plus 1 when you add 1, and then divided by 2. U plus 1 divided by 2. Okay? Now, I'm going to do the same thing for this, but I'm going to solve for dx. So if you think about this, to move dx, okay, to clear out this fraction, you'd multiply both sides by dx to move it over here. So what you'll have is du equals 2dx. But then to solve for dx, you would divide by 2. So you get dx, the derivative of x, is equal to the derivative of u divided by 2. Okay, so I'm not going to need that part. I just wanted to show you where this was coming from. Okay, what I essentially want you guys to see right now is this. We now have enough information over here to go in and replace every part of this integral. Okay, I can replace this x with u plus 1 over 2. And you'll see why. Just kind of bear with me here. I'm going to replace that x with u plus 1 over 2. I'm going to replace this square root with an exponent of a half, but I'm also going to take 2x minus 1 and I'm going to replace it with u. Okay? And now here's kind of the especially weird part. You're going to replace that with u plus 1 over 2. You're going to replace this with u, and dx, the derivative of x. Now as soon as we plug in u's, now we're not talking about x's anymore. Now we need to talk about the derivative of u. So what can we replace the derivative of x with so that we have the derivative with respect to u so we can integrate this? Dx is du over 2. So we have du over 2. To do true substitution, this is what we're actually getting at. We have to replace the x, this expression with x, and the derivative of x, all in terms of u, so that we can integrate, and then eventually we'll substitute back in our original stuff, okay? So if I want to clean this up, basically what I'm going to do is I'm going to take both of these fractions that are over 2, 2 on the bottom, 2 on the bottom. This is all multiplication here, essentially. So 2 times 2 on the bottom would be a 4. I'm going to pull 1/4 out front. Okay? So that I no longer have fractions that I have to actually worry about, okay? So I've got now u plus 1, right there, there's the u plus 1, times u to the 1/2, and the derivative with respect to u. So now this is a true function in terms of u. Basically, all I have to do now is distribute this u to the 1/2 into these parentheses, okay? So I've got 1/4 and the integral. This is u to the 1 times u to the 1/2. That becomes u to the 1/2 or 3/2, plus u to the 1/2 times 1 is u to the 1/2 with respect to u. And now basically what I have by substituting in all this other extra stuff, because again, the reason I had to do true substitution here is because this portion of the expression was not actually the derivative of the inside, okay? What I have now is just two u terms that I can easily integrate. How do you integrate u to the 3/2? You bump its exponent up by 1, and then you put it over that exponent. So this is going to become u to the 5/2 over 5/2 plus u to the 3/2 over 3/2, okay? With a essentially with a 1/4 out in front of it. Okay, so at some point here, I'm going to have to distribute 1/4, but what I'm going to do, because I didn't quite leave myself enough room here, I'm going to do a couple things all at once here. I'm going to pull this down over here, okay, and I'm going to change this to 2/5 times u instead of u divided by 5/2. I'm going to turn it into its reciprocal, okay? But I'm also going to substitute, well, actually, no, let's not do that just yet. Okay, let's see if you guys can follow me here with 2 steps at once. I'm going to turn this into 2/5, but then I'm going to distribute 1/4 to it. So 1/4 times 2/5 is going to be 2/20 or 1/10 u to the 5/2. Okay? Plus, okay, now this would be 3/2 u to the, or excuse me, 2/3 u to the 3/2, but when I multiply it by 1/4, 2/3 times 1/4 becomes 2/12 or 1/6 u to the 3/2. And if we're thinking about true integration, we want to not forget that we have to put plus c for our constant, or to make up for our constant. And then at the very last second here, the very last thing that we're going to do, now that we've actually integrated this thing in terms of u, now we're going to substitute what u actually is. So now we're going to put, whoops, it's not 1/2, it's 1/10. We're going to put 2x minus 1 back in for u. So 2x minus 1 to the 5/2 plus 1/6 2x minus 1 to the 3/2 plus c. And this is how the back of the book is going to represent it. So we're at a point where kind of I guess our luck is going to run out essentially. We're not going to end up with integrals where we have 2 separate expressions where one of them is a direct multiple of the derivative of the first one, okay? It's going to be the same thing down here. We're going to run into the same thing on this one, and actually I'll probably move this one to a separate sheet of paper just so I can fit it all. Actually, I could probably fit it all underneath here. But there's going to be that problematic thing, and here's the problematic issue with this one again. So x minus 4 is our larger expression. That's got to be our u. Okay, u is x minus 4. The issue is the derivative of u with respect to x is just 1. Okay, so when you differentiate x minus 4, you just get 1. However, the other portion of the expression is an actual variable. It's not just a multiple or a coefficient different, it's a true variable difference. So this is where, again, just like in example 2, we have to use true substitution. So not only do we pull u off to the side and say u is the expression x minus 4 and its derivative is 1, we have to take both of these and manipulate them so that we have something not only to plug in right here. So my integral is going to be, instead of x minus 1/4 to the 1/3 power, it's going to be u to the 1/3 power. I have to be able to substitute something in for x and something in for dx. So we get that from these 2 expressions right here. If you add 4 to this side, you get x equals u plus 4. So this x I can replace with u plus 4. Okay? Dx. Again, you would multiply dx on both sides to move it over, so you'd get du equals 1 dx, but then you would, well, I guess essentially you'd be done at that point. You get du equals 1 dx, so dx this time can just directly get substituted with du. You have to take your original expression or your original integral and replace everything involving x with something involving u. So you replace x with u plus 4, x minus 4 to the 1/3 with u to the 1/3, and dx with du. It's a little bit nicer here because you didn't have fractions, so you didn't have to pull out anything. Okay? All we do now is we distribute u to the 1/3, so we get u to the 4/3 plus 4u to the 1/3 du. And as soon as we get that, we have basically a polynomial in terms of u. So now we can integrate this, all right? Bump up the exponents by 1, put them over that new exponent. So this becomes u to the 7/3 over 7/3 plus 4u to the 4/3 over 4/3 plus c. Turn these into coefficients. So this is 3/7 u to the 7/3 plus 3/4 times 4 u to the 4/3 plus c. So in this case, the 4's will cancel, which is nice. So you get 3u to the 4/3. And then the last step is to rewrite it in terms of x, because we're originally trying to integrate a function in terms of x. So this becomes 3/7. Okay, what was u? It was x minus 4 to the 7/3 plus 3x minus 4 to the 4/3 plus c. Your last 4 questions today, this is how the back of the book is going to have them written. And it's because your 2 expressions are not directly related, okay? They're not just, one of them is just a multiple of the derivative of the other one, okay? They're both going to have x's in them when in fact the derivative does not have an x in them, okay? It's just the last 4 that are like this. All the rest of them are just extra practice for what we were doing on Wednesday, and also something kind of like this one. I think there's 2 of them that are similar to this first example, okay? So, one more day of substitution. Just let me know what questions you have. Try and get to this shortly after watching this video so that it's kind of fresh on your mind. Shoot me your questions right away, and then I'm totally fine if we have a collection of questions that we need to look at on Monday's clarification video. Okay, so we'll finish this out, and then we actually only have 2 more sections we have to do. We've got to do section 3 and section 4. We'll do those on Tuesday and Thursday next week, and then we will wrap up grades at that point. All right, guys, have a great day and a great weekend. Let me know what your questions are, and I will talk to you guys on Monday.